Hi students, I am Balaji Kosari. So in the previous class we discussed how to reduce a canonical form, how to reduce a quadratic form to canonical form by using orthogonalization or orthogonal transformation. So here are the few more examples of that. So they are 3x1 squared plus 3x2 squared plus 3x3 squared plus 2x1 x2 plus 2x1 x3 minus 2x2 x3. So this is the quadratic form. We need to reduce it into canonical form by orthogonalization. So simply, first of all, we have to construct a symmetric matrix capital A, right? So which is formed by the coefficients, respect to coefficients. So in the class we discussed how to remember these things. So he in this instead of x1 x2 x3 they are considering xyz, so no issue, you can take x1 x2 x3. Okay, so here we get the coefficient of x1 squared, coefficient of x1 x2 by 2, here coefficient of x1 x3 by 2, similarly for the remaining row 2 and row 3. So then we get matrix capital A. So first row is 3 1 1 and second row is 1 3 minus 1 and third row is 1 minus 1 3. So for orthogonalization or orthogonal transformation, we name model matrix which is formed by the normalized eigenvectors. So these normalized vectors are formed by the eigenvectors. So for that we need to find the eigenvectors. So eigenvectors comes from the eigenvalues. So eigenvalues are coming from the characteristic equation. So if the matrix of order is 3 by 3, then what is the characteristic equation? So the characteristic equation is lambda cube minus s1 lambda square plus s2 lambda minus s3 equals to 0. So here s1 is the trace of capital A and s2 is the sum of minus of principal diagonal elements. So you can see here clearly. So this is the diagonal, sum of minus of diagonal, and s3 is the det of capital A, so that is 16 here. So you can find that. So finally trace s1 is 9, s2 is 24 and s3 is 16. So let's frame the characteristic equation. So that is lambda cube minus 9 lambda square plus 24 lambda. So here lambda is missed, so don't worry, you can write it later. So 24 lambda minus 16 equals to 0. You can solve it by using a scientific calculator or Casio, or you can solve it manually also. So this is the synthetic division, so you can find it. So lambda equals to 1 is the one root, and by using that root you can reduce the quadratic form, cubic equation to quadratic form. So anyway, finally we get the characteristic roots or eigenvalues. So lambda equals to 1 comma 4 comma 4. So in the previous class we discussed for the lambda equals to 2 3 6, right? So there is a difference. Okay, so next step is we need to find the eigen vector. So for lambda equals to 1, so for lambda equals to 1, that is a minus 1i into x equals to 0. So a minus I equals to 0. Simply we get 2 1 1 1 2 minus 1 1 2 minus 1 1 minus 1 2 minus 1 and 1 minus 1 2. So unknowns are x1 x2 x3, so 0. So reduce into echelon form by using elementary row operations we get. So we need to, so we know all this process. So after using these row operations we get it in echelon form. So this is in, so simply we can write it right, rank of the matrix is capital A, or otherwise we can write it like this also. So algebraic multiplicity is 3 minus 2. If we are confusing here, you can follow the previous our class process. Okay, if you are not confused, you can follow this process. So algebraic multiplicity is simply right. So here what is the rank here? rank of this is, let's say, rank of B. So rank of B is 2, right? So algebraic multiplicity is, so sorry, geometrical multiplicity. So this is the geometrical multiplicity in the sense n minus r. Here n is 3 and r is 2. Rank of the matrix is 2. So A is equals to number of constants. So required number of constants are 3 minus 2. Number of non-zeros, so that is 1. So we can consider x3 equals to k. So if you are confused, you can simply follow our we proceed one method, right? So you can follow that method. So okay, so simply by back substitution we can solve that. So we get the capital X1 equals to, so x1 x2 x3, simply substitute this x1 x2. So we get the eigenvector lambda, eigenvector minus 1 1 1 for lambda equals to 1. So similarly for lambda equals to 4 we have to find the eigenvector. So simply by using the elementary row operations we are going to reduce that. So we will reduce this matrix capital. So same process we get this. So number of non-zero solutions n minus r. So n is number of unknowns. Here 3 unknowns are there. So and the rank of this matrix, so rank is simply 1. So 3 minus 1 2. So let's take this last two elements. So x2 equals to k1 and x3 equals to k2. You can simply consider any constants. So here they consider p q, so no issue at all. So simply we can solve by back substitution. If you, from row 1 x1 minus x1 plus x2 plus x3, so likely we get the, we can solve if we solve the above equation we get the x1 x2 x3 value. So for lambda equals to 4, these are the eigenvectors 1 0 1 and 1 1 0. So in the previous class we discussed for the distant eigenvalues 2 comma 3 comma 6. So by Noun theorem they are the distant eigenvalues are forms a orthogonal eigenvectors, mutually orthogonal eigenvectors. But here the resultant eigenvalues are repeated eigenvalues. They are 1 comma 4 comma 4. So we need to check the condition for the orthogonalization. So first of all, what is orthogonalization? So orthogonal matrix. So simply we know that, right? Let's say capital matrix, capital A is there, order of the matrix is n. So if we say that the matrix capital is say to be orthogonal, how can we say that? A into A transpose equals to identity. So this is a square matrix, right? So here, but the eigenvector is column matrix. So for that we get simply 0. So condition is, if we multiply x1 transpose, so x2, if we get I0, then x1 comma x2 are mutually orthogonal. So let's check. So we have how many eigenvectors are there? x1, x2 and x3. So we need to check these three are mutually orthogonal or not. So first we have to check x1 with x2 and x3. After that x2 and x3. So how many times are there? So first one is, so x1 x2 and x1 x3, and the third one is x2 x3. So these three are orthogonal. Then the given then the x1 x2 x3 are orthogonal to each other. So let's do that. So we have an eigenvector side x1 x2 x3. So x1 is minus 1 1 and x2 is 1 0 1 and x3 is 1 1 0. So let's check that. So x1 transpose x2, so this is the x2 x1 transpose, and this is x2. If we multiply minus 1 into 1 minus 1, 1 into 0 1, plus 1 into 1, so minus 1 plus 1 0. So what we get, x1 transpose into x2 equals to 0. Next, x1 and x3, right? So x1 transpose into x3. So we have x1, and here we have x3. So if we multiply that, minus 1 1 into 1 0 0, we get 0. Okay, so and the remaining thing is we discussed here, right? And x2 and x3. So that for that, x2 transpose into x3, we have x2 101 and x3 110. So if we multiply that, we get the 1. So what I told in the beginning, so these three eigenvectors x1 x2 x3 are mutually orthogonal. When we said that these three, x1 transpose x2 equals to 0, x1 transpose x3 equals to 0, and x2 transpose x3, both these three are 0, then we can say that capital X1 x2 x3 are orthogonal. So this is not orthogonal, right? So which one is not orthogonal? This x2 is not orthogonal. That's why, so we have to find that orthogonal vector. So for making orthogonal eigenvector, so we need to find a eigenvector, new eigenvector. So here, when it is failed, x2 transpose and into x3, which is equals to 1, which is not equals to 0, so that's why it's failed. So we have to find that eigenvector. So let's define a new eigenvector. Capital X2 equals to ABC. Okay, so let's do that. We have, right? So we have to check this. So we have to check this x2 with x1 and x3. So simply we have to check this x2 with x1 and x2 with x3. So first one, x2 transpose x1. So x2 transpose x1. So x2 transpose is in the sense x2 we have ABC, right? So this is x2 transpose, and x1 is same previous vector, minus 1 1 1. So if you multiply these two, if it is orthogonal, x2 transpose x1 equals to 0, right? So equals to 0, that implies minus b plus c equals to 0, and remaining case x2 and this x2 and x3. Remaining case is x2 x3. So x2 we have ABC, and x3 simply we have this, right? So this is x3 1 1 0. If we multiply ABC and 1 1 0, we get a plus b plus c equals to 0. So here one thing is missed, 0, that implies here also 0, that implies, because x2 x1 are orthogonal, x2 x1 is orthogonal and x2 x3 is orthogonal, right? Make them orthogonal simply. So for that we get a plus b equals to 0. From a plus b we can write like this, right? A equals to minus b. Okay, so a equals to minus b, and we have the equation minus a plus b plus c equals to 0. So simply from the equation so simply let's take a non-zero value, small t, and t belongs to capital R. So let b equals to capital T, and then a equals to minus t, right? So if we put this in this equation, minus b plus c plus minus a plus b plus c equals to 0, we get the value of capital C. t plus c equals to 0, so c equals to minus 2t. So what is the capital X2? X2 is the new X2, a, b, c. So x2 equals to a, b, c. A is minus t and b is t and c is minus 2t. So minus t, if you take minus t or t, you can take anyone, t or minus t. So if you take minus t, 1 minus 1, 2. So the linear independent eigen vectors are, so x1 is common, and here x2 is the this one only. So above find x1, this is the value of x2. So if we check this x1 transpose x2, x1 transpose x3 and x2 transpose x3, we get all cases we get 0. So because this is a modified eigenvector, right? So this is a orthogonal eigenvector. So we know that each normalized eigenvector. So let's say for the normalized vector n1, so which is, so n1 equals to capital X1 by norm x1. So each of the element in the eigenvector which is divided by its length of the its eigenvector, right? So that is, so this is the normalized vector n1, this is normalized vector n2, and this is normalized vector n3. So simply we get the model matrix P, which is formed by the normalized eigenvectors. So let's check the orthogonal. D equals to P transpose. Let's forget this. So D equals to P transpose AP. We have the value of P, right? This is the P. So if we write the rows and columns, rows as columns, columns as rows, we get the transpose of the matrix. So this is the matrix P transpose. This is the capital A matrix, and this is the P matrix. So this page is repeated, don't worry. So simply, so if we multiply last these two matrices, we get this matrix. So if we solve this, we get 1 by root 3 . So this is minus 1 by root 3. Okay, so minus 1 by root 3, 4 by root 6, 4 by root 2, 1 by root 2, 1 by root 3, minus 4 by root 6, 4 by root 2, and 1 by root 3, 8 by root 6, 0. So simply if we multiply these two matrices, we get this matrix, that is 3 by 3, 0, 0, 0, 24 by 6, 0, 0, 0, 8 by 2. So simply we get the diagonal matrix 1, 0, 0, 0, 4, 0 and 0, 0, 4. Here the diagonal matrix capital D is the spectral matrix. So the canonical form is Y transpose dy. So here we know that, right? So Y is a linear transformation of capital Q. The canonical form is Y transpose dy. So Y is a unknown matrix, right? So Y is, so order of the matrix is 3, right? So that's why, so y1, y2, y3. So y1, y2, y3. So simply we get, so previously we write a matrix form to quadratic form, right? So you can simply use that. First we write the equation for the quadratic diagonal elements. So that is, so y1 square plus 4y2 square plus 4y3 square. So simply from here we know that, right? So nature of the quadratic form is, so here all the b terms are the positive. So the nature of the quadratic form is positive definite. So rank of the matrix, so here all the b terms 1, 4, 4 are 4 are non-zero. So rank of the matrix is 3. So natural index of the quadratic form. So what is the index of the quadratic form? So the number of positive eigenvalues. How many positive eigenvalues are there? 1, 4, 4. 3 eigenvalues are there. So next, signature of the quadratic form. So what is the signature of the quadratic form? Simply we have, right? So number of positive b terms minus number of negative b terms. So positive b terms is 3 and remaining negative terms is 0. So 3 minus 0 equals to 3. So like this we can find the, so this is the special case. Okay, we can expect a log from this. Okay,